Hello everyone, in this video we will cover the section 4.6. In this section we will see the rank of a matrix. This is the last section of the chapter 4, and then after this section we will continue with the chapter 5 in the next videos. Okay, if a matrix A is an n by n matrix, each row of A has n entries and thus can be identified with a vector in Rn, since we have n components for each row of the matrix A, so each row of this matrix can be considered as a vector in Rn. The set of all linear combinations of the row vectors is called the row space of the matrix A, and it is denoted by row A. We have another special space in this section which is denoted by row A, and it is the set of all linear combinations of the row vectors of the matrix A. For example, we have here 1, 0, minus 2, 4, 3, 2, 2, 1, minus 1, 2, 0, 3. So how many rows do we have for this matrix? We have 3 rows and 4 columns. And every row has 4 entries, as you can see. Therefore every row is a vector in R to the 4. Here n is equal to 4, and the row space of this matrix is the set spanned by the rows of the matrix A. If, let's say, the first row is R1, the second is R2, the third one is stated by R3. So row space of the matrix A is a set spanned by the vectors R1, R2 and R3. Okay, this is called the row space. Each row has n entries, or for this matrix we have 4 entries since we have 4 columns here. Row space is a subspace of Rn. So for the example, it is a subspace of R to the 4. And since the rows of the matrix A are identified with the columns of the transpose of the matrix A, so we could also write column space of the transpose of the matrix A in place of row space. In other words, row space of a matrix also can be considered as the column space of the transpose of the matrix A. If you remember, the transpose of a matrix has columns which are the rows of the matrix A. The rows of this matrix become columns of the transpose of the matrix A, if you remember. Okay, by the way, let's remember the other special subspaces here. What was the definition of the column space? If we say the first column is stated by A1, the second column is A2, the third column is A3, the last one is A4. If you remember the column space, let's write here. The column space of the matrix A is a set spanned by the columns of the matrix A1, A2, A3, and A4, and after finding the echelon form of this matrix, we may remove some of them, since we don't have pivot positions in these columns. And we find also the basis by following this way for the column space. And for the null space of the matrix A, it is the collection of all vectors, let's say x, such that they satisfy the homogeneous equation here, where the matrix A is the coefficient matrix. Okay, so we have three special subspaces: column space, null space, and row space. Row space is a subspace of R to the n, namely we look at the number of columns, and also for the column space, it is a subspace of R to the 3, namely we look at the number of rows, because every column has 3 entries for this matrix. And generally we write column space is a subspace of R to the m, namely we take the number of rows, okay, R to the 3. For the null space, so every vector should satisfy this homogeneous equation, and the size is n by n generally. And to define the matrix multiplication here, so x should have the size n by 1. We should get the common number n. Therefore we will have n entries, if you remember. Therefore the null space is a subspace of R to the n generally. For the example, n is equal to 4, so the null space is also a subspace of R to the 4, which means that the number of components of a vector in this space is 4. Okay, so we have an important theorem here. If two matrices A and B are row equivalent, then the row spaces are the same. We get the same space for the row equivalent matrices. If B is in echelon form, the non-zero rows of B form a basis for the row space of A as well as for that of B. Okay, to find a basis for the row space of the matrix A, first we need to find its echelon form, and we take the non-zero rows of the echelon form of this matrix to find a basis. Okay, I will not talk about the proof of this theorem, so let's see directly an example about that. So find basis for the row space, the column space, and the null space of the matrix given here. This may be a final question, therefore you should listen, you should watch carefully. Okay, we want to find basis for the row space, column space, and null space of the matrix A. To find basis for the row space and column space, we need to find the echelon form of this matrix. After doing row operations, you will see it is row equivalent to this matrix, which is the echelon form of the matrix A. So when we look at this matrix, we have a pivot position in the first row, we have a pivot position in the second column, first column, second column, and we don't have any non-zero number here for the third column, but for the fourth one we have a non-zero number here. Okay. To determine the pivot positions, other way is to find the leftmost non-zero numbers for the rows. Okay, this is the leftmost non-zero number for the first row, and this is the leftmost non-zero number for the second row, and so on. So A1 has the pivot position, A2 has the pivot position, and A4 has the pivot position. And when we look at the rows, this is the non-zero row R1, this is the non-zero row R2, and this is the non-zero row R3 for the echelon form. Echelon form. Therefore, basis for the row space A beta row A contains the vectors which are the first row, second row, and third row of the echelon form, not the matrix A itself. Okay, so R1, R2, and R3, and from here we can understand the dimension of the row space is equal to 3. R1 has the components 1, 3, 1, 1, 3, minus 5, 1, 5, and thus we write the second row clearly 0, 1, minus 2, 2, minus 7, and the third row has the components 0, 0, 0, minus 4, 20, and we have 5 entries for each one. Therefore it is a subspace of R to the 5. Okay, for the column space, a basis for the column space contains the vectors A1, A2, and A4. Okay, and dimension of the column space is 3. Which means that we can remove A3 and A5 from the definition. It is enough to define the column space by taking the first, second, and fourth columns. This is the set spanned by the columns A1, A2, and A4. Okay, and you see basis for the column space. By the way, of course we don't take the columns of the echelon form. We take the columns of the matrix A, A1, A2, and A4. Okay, you see we write the components of the columns of the matrix A, minus 2, 1, 3, 1, minus 2, 1, 3, 1, minus 5, 3, 11, 7, minus 5, 3, 11, 7, and 0, 1, 7, 5, 0, 1, 7, 5. When we write a basis for the column space of the matrix A, not these ones. Okay, not these ones. But when we write a basis for the row space, we take the rows of the echelon form of the matrix A. Okay, we take directly these rows, not the rows of the matrix A for the row space, to write a basis, but for the column space we take the columns of the matrix A itself. Okay, this one, and this one. You should see the difference between them. You should be careful. Okay. Notice that any echelon form of the matrix A provides a basis for the row space of the matrix A and also identifies the pivot columns of the matrix A for the column space. However, for the null space we need the reduced echelon form, or also we can determine directly the structure of the vectors in the null space by using this echelon form, or to make easier the calculation you can find the reduced echelon form. Here you can see the answer for the null space by using the reduced echelon form, but I will find the answer by using the echelon form directly. Okay, so by using the third row, by the way, we have 5 unknowns: x1, x2, x3, x4 and x5. x3 is free variable, x5 is free variable. Therefore we will write the basic variables in terms of the free variable by using the third row. So we can write minus 4x4 plus 20 x5, for x4 plus 20 x5 is equal to 0, and using the second row, 1 minus 2, 2 minus 7, 1 minus 2, 2 minus 7, so we write x2 minus 2x3 plus 2x4 minus 7 x5 is equal to 0, and 1 3 minus 5 1, 1 3 minus 5 1, 3 minus 5 1, 5, I guess. Okay, so we have x1 plus 3 x2 minus 5 x3 plus x4 plus 5 x5 is equal to 0. What are the free variables? Let's check again. x3 and x5 are the free variables. x3 and x5 are the free variables. So using the first one, x4 is a basic variable, and x4 becomes 5 x5 by using the first equation. x4 is 5 x5, namely we find x4 in terms of the free variables. And from the second one, x3 and x5 are free. We can write x4 in terms of the free variable, which is 5 x5. And from the second equation, we can find x2 in terms of the free variable. So x2 is equal to 2 times x3 minus 2 times x4 becomes minus 10 times x5 plus 7 times x5. Therefore x2 is equal to 2 times x3 minus 3 times x5, and using the first one we can find x1, which is equal to minus 3 times x2, namely, let's write directly, minus 3 times x2, namely minus 6 times x3, plus 9 x5, minus 5 plus 5 x3. We write the terms to the right side, minus x4, namely minus 5 x5, minus 5 x5, and from here we obtain minus x3 plus minus x5, I guess, minus x5. Therefore, the solution of the homogeneous system can be written as x1, x2, x3 x4 and x5. So x1 is equal to minus x3 minus x5, this is x2, x2 is equal to 2 x3 minus 3 x5, x3 is 3, x4 is 5 x5, x5 is 3, and from here we can write x3 times, we use the coefficients, minus 1, 2, 1, 0, 0, plus x5, minus 1, minus 3, 0, 5, 1. If we say this is v1, this is v2, so a basis for the column space, for the null space, for the null space contains the vectors v1 and v2, and the dimension of the null space is the number of the free variables, and clearly you see we have two vectors in the basis, so we have two free variables. The dimension of the null space will be 2. Okay, and you see from here also you will see. Okay, observe that unlike the basis for the column space, the basis for the row space and null space of the matrix A have no simple connection with the entries in A itself. We don't have any clear connection between the basis for the row space and null space of the matrix and the entries in the matrix A itself. So here we have an important definition. The rank of the matrix A is the dimension of the column space of A, and it is denoted by rank A is equal to the dimension of the column space of the matrix A. And you know, the dimension of the column space is the number of pivot positions. So this is also equal to the number of pivot positions. the number of pivot positions. So since row A, the row space of the matrix A is the same as the column space of the transpose of the matrix A, the dimension of the row space of A is the rank of the transpose of the matrix A. The dimension of the row space, is the number of non-zero rows of the echelon form of the matrix A, you know, or we can find this is equal to rank of the transpose of the matrix A, since row space of the matrix A is equal to the column space of the transpose of the matrix A, and you know this is equal to also from the definition rank of the transpose, okay, of the matrix A, since we have the column space of the transpose of the matrix A. And the dimension of the null space is sometimes called the nullity of A. And here we have very important theorem. The dimensions of the column space and the row space of an n by n matrix A are equal. This common dimension, namely the rank of A, also equals the number of pivot positions that I said here in A, and satisfies the equation written here. So let's see clearly all information about the dimensions for the special subspaces. Okay, from the theorem, that we saw here, this one, the dimensions of the column space and the row space are equal. So the dimension of the column space and the dimension of the row space equals each other. Okay. Also, this is equal to the rank of the matrix A from the definition of the rank. Okay. From the definition, it is equal to the dimension of the column space. Let's see. The rank of A is the dimension of the column space of the matrix A. Therefore, we can write this term also. And we know since the dimension of the column space is equal to the number of pivot positions, so to find all of them, it is enough to find the number of pivot positions. The number of pivot positions. And also we know from the theorem the addition of rank A and the dimension of the null space is equal to the number of columns. Or let's write in this form, where A is n by n matrix. Okay, the rank A plus dimension of the null space of the matrix A is equal to the number of columns, the second number in the size, as you can see. For example, if A is 7 by 9 matrix with two-dimensional null space, example 1. A is 7 by 9 matrix, and we know the dimension of the null space of this matrix 2. So what can we find using this information? So we can find rank of the matrix A. And what is the question? Let's see. What is the rank of A? What is the rank of A? Easily, from this equality, from here, we know this is equal to 2 and n is equal to 9. The rank of the matrix A is equal to 7. This is equal to 7. Easily we can find by using the theorem. The second question for the same example: could a 6 by 9 matrix have a two-dimensional null space? Two-dimensional null space. So we know rank A plus dimension of the null space is equal to the number of columns, which is equal to 9. And could we have two-dimensional null space for this matrix whose size is 6 by 9? When we write 2 for the dimension of the null space, rank A becomes 7, which means that we should have 7 pivot positions. 7 pivot position, but the columns of B are vectors in R to the 6, and so the dimension of the column space cannot exceed 6. That is, rank B cannot exceed 6. When we look at the matrix, the size of the matrix A, which is 6 by 9, and you know the column space is the set spanned by the columns of the matrix A, and when we look at the number of rows for the matrix A, we have 6, which means that every vector in the column space has 6 entries. Therefore, the dimension of the column space of the matrix A should be less than or equal to 6. It cannot exceed the number 6. Okay, but here we have 7 for the rank of A, which is also equal to the dimension of the column space. Therefore, we have a contradiction here. 6 cannot be equal to 7. This is a contradiction. This is impossible situation. Therefore, we cannot have two-dimensional null space for the matrix A whose size is 6 by 9. The answer is no. Okay, because of this reason. And here we have an important theorem, which is the continuation of the invertible matrix theorem. A is n by n matrix here. To talk about the inverse of a matrix, so we should take square matrices. We should interest in square matrices. Then the following statements are each equivalent to the statement that A is an invertible matrix. The columns of A form a basis of Rn. The column space is equal to Rn if the columns of the matrix A form a basis for the vector space R to the n. Okay, and we know column space is a set spanned by the columns of the matrix A. So we have n vectors here, and the columns of A form a basis for Rn, which means that all of them are linearly independent, which satisfy the first condition. And we can write every vector in Rn as a linear combination of the vectors which are the columns of the matrix A, which means that the column space of A is equal to R to the n, the space itself, the vector space itself. And all columns of the matrix A are linearly independent, so the number of pivot positions will be the number of columns, which is n. Therefore we can obtain this result, and the dimension of the column space is equal to rank of the matrix A. Okay, and if we have n for the rank of the matrix A, from the theorem, from the previous theorem, we know the rank A plus the dimension of the null space is equal to n. This is equal to n, so we have 0 for the dimension of the null space, and we have the only vector space whose dimension is equal to 0, so this is the 0 vector space. Therefore null space of A will be the 0 vector space, so we obtain this thing, and the dimension of the null space is equal to 0 from here. Okay, all of them are equivalent. If you have one of them, the others automatically satisfy. And lastly, we have an example here. The matrices below are row equivalent. You see the matrix A and its echelon form B is written here. We have already. Find rank A and dimension of the null space. Rank A is equal to the dimension of the null space, which is also equal to the number of pivot positions. We have 2 pivot positions here. Therefore, these ones are equal to the number of pivot positions. And dimension of the null space can be obtained by using the formula obtained from the theorem, which is actually rank A plus dimension of the null space is equal to n, you know, and the dimension of the null space is equal to 3. And also we can find directly basis for the row space and column space by using the echelon form. So we write the rows, namely basis for the row space of A is equal to R1 and R2, namely this one and this one. We don't take the rows of the matrix A for writing the basis for the row space, and for the column space, the basis for the column space, we use these columns. Okay, the first column and the second column have pivot positions, so we write A1, A2. Okay, A1, A2. Thank you very much for your listening.